Hello. In the previous video, we had some quarrel and some adventure with the unjustifiable calculations, the fictitious calculations about the closed solutions of the universe, which the closed geometry corresponding to the sphere expanded to all directions with the same rate, so the radius is increasing linearly with time, but we have assumed that the universe is filled with non-relativistic matter, so the expansion rate of this sphere, which is describing and improvisating the Gauss surface, which the source is a gravitational material inside of it, embedded into it, so you have some gravitational field, and which the field is not stationary. The field is not stationary, it is because the motion of the source, the mass, the gravitational masses are moving inside. So the field that we were solving and interested in was actually non-conservative field. So it cannot be expressed as the conservation theorems. Okay, you need some other terms, constants actually, and all right. Well, we have seen that the expansion is determined and by the density of the fluid, the cosmological fluid, and the geometry, the shape of the universe. So the fields, well, those are actually all the solutions of the field equations, but we haven't seen them yet because I didn't record anything about the tensors and the tensor algebra. So it's going to be, well, I might be impeachable for doing such a thing or continuing with such a preference to talk about the field equations, even they're tensorial, like you see in the right behind me. It's better for us to continue with the Newtonian dynamics of the cosmology because we are doing standard cosmology, right? All right. In the previous video, we have calculated the total lifetime, right? The time that is required the universe to evolve from the Big Bang, t equals 0, to the some moment of time. So we have actually introduced the conformal time, but we will do it right now in this video. But the problem was that we had a little bit different integral compared to the flat case of different kind of fluids, radiation, non-relativistic matter in the flat universe. So our solutions are different, not something linearly or near to the linear. It was actually t to the half over 3, 2 over 3, and t to the half. You remember that? But if you can remember, what we have reached and deduced was actually the cosine and sine functions corresponding that the universe is behaving like an oscillator, the harmonic oscillator. It is due to our assumption that the universe is expanding in all directions with the same rate, so the rate is not changing, but the rate itself is determined by the fluid density. It's corresponding to the Einstein's stress tensor, energy and momentum tensor, which is corresponding that the first indice is the flow of energy and the other one is the momentum. And depending on the time-like or space-like coordinates, the values are going to be changing. And it is because it's interchangeable, right? All right. What we have seen that the universe is behaving like a harmonic oscillator, corresponding that, if you could remember, that in our integrals in the previous video, inflationary cosmology, the fourth video, we had an integral. We defined some parameters, right? We changed the variables so as to make it solvable, or it's fallacious, I know, but we have to do this. This is our requisition. This is compulsory. We need to define the followed integral we have seen. we were in the very requisition to write down the integral we have solved in the form of change of variables. So we have seen there are some theta, the angles. Those angles are corresponding to the development angles of the universe. Because you want to know, because we have a function which is harmonic function, sines or cosines, and we are looking forward for the solutions which are dependent on the angles, and angles are the time, the functions of time. So those angles are corresponding to the developments and evolution of the universe, depending on the period of the time, which the theta, the angle, is defined between given angle intervals. Okay, so between the intervals 0 to pi, the universe grows, and you know how it grows. I mean, the rate of the rate of the inflation. And after the value, some critical time tc, we will do that in this video. This is just a summary in a nutshell. We will see that after some time, which is called critical time of the universe. Well, we have two critical times in the standard cosmology for this geometry, which is the radiation-dominated era when it occurs, and afterwards, the time proceeds on, the radiation density of the universe is at some time, some moment of time, it becomes equal to the non-relativistic matter density of the universe. So this is actually where the matter and radiation densities are equal. It's some era. They are closely each other. They are really close. At some critical time, they are equal, and afterwards, the matter density grows up. Maybe that will be the reason why the dark energy contribution is actually perturbated. I mean, it's like an impulse. We have dark energy in the previous eras of the universe, but we don't see that. We have the contribution there because the nearest scientific observation, it was actually James Webb Space Telescope on the March or April, I'm not sure. They observed some massive, supermassive black hole which occurred and existed. Afterwards, the Big Bang, it was actually corresponding to the matter-dominated era, but you have still radiation contributions. It is still visible in that era. So we are asking, how did it form on that very times? Because the conditions are not, the conditions of that very times, what we expected, are actually, these conditions did not allow to material to be densified into some region of space to form a supermassive black hole. So, how it happens, right? It's because due to our assumption we failed. The standard cosmology model is not giving you that very auspicious opportunity to explain the era, which is actually the inflationary era and the dark energy contribution. So we are doing it in the modern cosmology, and we need to fill the cages. So, okay, forget about that for now. It's really it's miraculous, I know, but we have we haven't finished the standard cosmology models like this one, so we have to continue, right? Otherwise, everything is succumbed and adrifted if you continue without any path, it's really hard. Well, you need to continue with some paths which are determined identically and assiduously, elegantly, so you don't distract it, okay? You won't be distracted easily. Otherwise, it's about, something dissuades you, and you cannot continue your work in cosmology because there are many bifurcated departments and fields in the physics, so you have to do it, or you have to start from something, okay? So this is actually what we are doing, standard cosmology. After that critical time, the universe is collapsing back, corresponding that the radius is getting smaller and smaller between the angle interval is pi to 2 pi. Universe gets smaller. It's because of the gravitation. Gravitational attractions of the universe, in the universe, are actually affecting the expansion rate. We have you can imagine that as we have a kinetic energy coming from the Big Bang, and which the energy is actually causing the universe to grow to the future. As it grows, the material density, because there are interactions, the charts, the fields, and the mass, the nuclei, the first primordial nuclei, they are forming, right? And as they are forming, the interactions and the number of interactions and the density or the strength of the magnitude of interactions are growing up. Those are actually the reasons why we are actually adding the contribution of the gravitational attractions on the very times of the universe. And those gravitational attractions tend to slow down the universe. Why? Imagine we have some balloon or something like a plastic bag, which is spherical, okay? Spherical. You have some fluid inside of it. It might be honey or maybe water, anything else. But we know that this water or fluid should be viscous. So as you try to move inside of this water or fluid, you will exert a resistive force in the opposite direction of your displacement. So the force you exert cannot be neglected because you are interacting with that. So your body tend to stretch it out as you move in the opposite direction of the resistive force. This fluid tends to distribute along this balloon or space or whatever geometry you are using with 100%. Every dot must be filled with this fluid. So if it were a bottle, then the water must be in this, the shape must be the same of the bottle, right? Same as it. So as it grows, as this space is increasing, the volume increases. So the water or the fluid, honey or whatever else, is try to move in the direction of the expansion, the displacement of the space, which is actually towards to the outside. But as the person or the material you are in this space, you have some motion in the, due to the Big Bang, you have also a kinetical energy, which you are trying to displace towards to the future, towards to the expansion, but the expansion is more faster than you, but the viscous term is not affecting you. Well, it affects, of course, locally it is, but the global scales, the net expansion is determined by the fluid. Imagine there are other people like you in this viscous water or fluid. So those people will try to come closer. Those are actually gravitational attractions. The gravitational attractions of the universe, which is actually which is actually there due to the presence of the gravitational materials. They tend to come closer because the gravitational forces are attractive. As they try to come closer in the viscous fluid, the rate of the expansion must be decreased. In the early times of the universe, the expansion is so rapid, so the gravitational attractions, after some moment of time of the early era, which the radiation-dominated era is past, elapsed, so we are talking about the matter densities which are dominant, but the universe is still expanding. Those gravitational attractions between the gravitational masses must must decrease or affect the expansion in the opposite direction. So the expansion must be slowed down by a factor of the magnitude of the entire all gravitational attractions of the universe. So until 1998, the universe was expected to be slowed down into some region of space, some time, which is actually called the critical time. Afterwards, the entire kinetic energy, which were actually coming from the Big Bang, must be balanced with the gravitational energy. It can be expressed or it can be elucidated or enlightened as spring and mass system. As you displace it, more displacement, if it is Hooke spring, which is actually saying it's a linear force depending on displacement. Imagine this is a constant, it's a wall, and there's a spring in here, and we have a mass. So I displace it by some delta x, for example. So the force is in the opposite direction. As I displace it further, more and more, the greater force I will exert, right? Not intend. It doesn't depend on my intentions. The nature, it doesn't care what we are thinking. So it is injudicious to think about that. As it moves away, the potential is increasing, right? Due to the spring constants and the mass they are interacting. So the greater the potential, greater the force, if we are talking about some conservative force. Otherwise, it's not possible to write down the force by the negative gradients of some scalar functions, but we need some other vector potentials actually, which can be, for example, the non-stationary electric field. Some gradient of some function, electric potential, minus the time derivations of the vector potential, the magnetic vector potential actually. This corresponds that after some time, the gravitational attractions and the corresponding energy, which is actually restoring energy, restoring force, will be balanced to the kinetical energy, which tends the universe to expand. But this expansion is prevented by the presence of the gravitational materials in the entire universe. So they are balanced. It starts to grow. The rate is decreasing. It flattens in some space, some region, some time, and it decreases. The moment that it starts to decrease is actually going to finish as Big Crunch. The universe is collapsing to some region, some singularity. We are actually doing this in this video, the theory of it. We did the mathematics in the previous video. In this video, we will talk a lot. But permit me then to continue with the solution of the consequences, okay? The solution of the integral we have solved. By the way, we solved it for the time that is required. So we need some critical moment of time. Afterwards, we will multiply it by the speed of light, c, and we will get the horizon distance of the universe at some final time. The final time is corresponding to the moment that the kinetical energy is equal to the potential energy, which is a critical solution. And afterwards, that final time, the universe will shrink down, collapses back, okay? And by doing that, what we will see, we will actually doing that. And afterwards, I will define some critical density function, which we will describe the expansion of the universe depending on the actual densities and the critical densities. Okay. All right. Our solution for the time, I am not going to solve it again. We solve it with respect to the time, conformal time. It was actually some constant in here, the alpha, which was 4 pi g rho m naught divided by 3kc squared. The k in here is 1, correspond to the closed geometry. Integral some x corresponding to the Big Bang starts from singularity. Our integral was actually x plus x of t dx of t. Well, we need some constant here. Let us take it here. And I'll write down solutions again. And 2 alpha x of t minus x squared of t. Is this correct? Sorry. 2 alpha squared. 2 alpha squared. Yeah. Okay. So we have found the solution of this integral was t. Well, it's actually the inverse cosine, right? If you can recall, it was actually okay. Yeah, it was the inverse trigonometric functions. So we describe it by using the boundary conditions. We have seen that the time that is required to the universe to evolve dependent to the development angle. We afterwards defined development angle by solving x, because we have seen that x was the function of a tilde, the scale factors, and it's also the functions of the cosine theta, right? 1 minus cosine theta. So we defined with the functions, the harmonic functions, cosines and sines. So we have we have this integral after this changing of variables. We have here, so theta naught to theta of t. It was dt actually. Sorry, it must be minus. Okay, it's more clear right now. So if you distribute it along, so we have theta, the sine, right? And we have the rates, well, it's positive sign, so we have negative sign in that place. We have the intervals, limits, lower limits to the theta naught. Well, let's say some constant c for now. I want to show you t. This is actually the evolution of it. We have alpha here. Alpha was actually, let me write down it again. 4 pi g, it was actually my previous notes. Rho m naught divided by 3kc squared. K is 1 in here. So theta of t minus sine theta of t. So it's a t. Well, I say the universe is expanding. Well, the expansion rate is decreasing as the time itself elapses to some critical time. Let's call this time t sub c. Is it visible from that place? I can write down there. Okay. Here can be used. Can use here. We call that some critical time corresponding to the critical angle, some theta value, the development angle of the universe, corresponding to the graphic actually. So we have, I'm not going to write down again, alpha, theta naught, for example, or c, some critical value, times sine theta c. Okay. This is actually necessity. If we know the time, for example, if you can recollect from this is closed geometry, closed matter dominated, matter dominated. We can have a revision of the previous cases. It was actually t. It was about a to the 3 over half. A was actually the scale factor, right? Well, but it's better for me to write down it in the form of scale factors. We multiply both sides by the speed of light, so you will get something in the units of length. Okay, it is actually horizon distance because in the previous cases, as you can remember, we did the same thing. We multiplied every side ct, so it gave us horizon length or physical distance. And it was actually, for example, the grades are t to the 1 over half for radiation dominated flat universe, and t to the, well, not equal, it's proportional, 2 over half, 2 over 3 for the non-relativistic matter dominated flat universe. But it's different than now. So as to find out the scale factor, we can write down without, it's not very that much. You can check because we did that. Some final value, let's say t, not the final value, a tilde t minus alpha. You can do that because we did this change of variables, so as to solve this integral, okay? It's not important. So I can multiply both sides by c, the speed of light, so c alpha. This is actually again a constant because we have c here. Theta, sine theta, which is actually giving you something in units of length. Meters per second times second is meters, so you have some physical range. At some critical time, let's say, I am pretty sure it is not visible from here, so it's better to write it smaller. C alpha theta minus sine theta, some physical length of function of time. At critical time, let's say Tc, so those are, we come into the C, and that's it. Oops, we have the same vicinity. If you calculate the scale factor afterwards, which can be expressed, we know the scale factor and its definition. I will show you another way, which we will solve it from here. Where is this? Well, let me say two different solutions with conformal time theory. d eta equals dt over a, and the same holds in here. This one is here actually, and this is another one. So we will keep going from here actually. I take that as equation. AT, but it was actually AT divided by K. Oh yeah. K to the half